Now we are going to approach a very famous part of game theory, of basic game theory, and that is necessary theorems for the existence of Nash equilibrium, in particular the existence of Nash equilibrium of mixed extensions of finite games. So here is the picture of John Nash. Probably you have heard about him. If not, you are welcome to read about him. So let us get to work. So why do we need an existence of Nash equilibrium? It's not just interesting; it's very important because, first of all, it means that in a way the game has a steady state. It has a state where nobody has a reason to deviate, given that others don't deviate. It's a very reasonable way to define a steady state. Another thing is that having an equilibrium means that when we talk about the properties of equilibrium, we are not talking vacuously. And we don't even need to find equilibrium. There is a reasonable argumentation behind saying something about equilibrium, because we are sure they exist. At least one, if we know about existence. And the last part is that if we know that there is existence and we set to find an equilibrium using some algorithm, whatever, at least we know that we should be, at least we know that there is a hope to find an equilibrium. So maybe it will take a lot of time, and in general, we won't study this in this course, but it can be proven that the general problem of finding an equilibrium, even when we know it should exist, is general. It's very hard, so we can reduce many hard problems to that problem. But at least we know that an equilibrium exists. So having, I hope, convinced you that it's important to know about the existence of Nash equilibrium, let us talk about existence. So first, I remind you that Nash equilibrium can exist or not, both in finite and infinite games. So in finite games, in the case of traffic coordination, the Nash equilibrium exists. That's when they both coordinate on either to both use the left or either both use the right lane. So this is a finite game with two strategies for each player. One Nash equilibrium exists, and Nash equilibrium exists, and actually here we have two equilibria. So in this, actually we're going to talk about at least one exists. Does it exist? But here we have even two. And the famous matching pennies game is one where we don't have an equilibrium from any state we would like to change. There is at least one player, actually exactly one, the guy who gets the 0, who can change and get 1. So when we both play A, the second player can play B and get 1. When they play AB, the first player can play B and get 1. When play BB, the second player can play A and get 1. And when they play BA, the first player can move to A and get 1. And from this state, we already saw that the second player can move to B and get 1. So there is this, we can say, vicious circle, or more formally, it's a finite improvement path which is circular, and therefore it can be made to be infinite. So it's actually infinite improvement path, and therefore since that is it's not necessary that you have such a path if we don't have an equilibrium, but in this case, since this path exhausts all the possible states, we don't have an equilibrium. So an Nash equilibrium can either exist or not. These examples show finite games. In one it exists, in the other one it doesn't. and it also can exist not in infinite game. So, for example, consider the game with some exercises on tutorials, and you have two players. Each one has the strategies which are all the numbers between 0 and 1, and the utility of both players is just the product of those strategies. I'm waiting, by the way, before I give you the answer whether the Nash equilibrium exists, and if yes, what it is, and if not, why. So if you wish, you can always pause the video and try to exercise to process this yourself. In this case, a Nash equilibrium does exist, and actually the set of Nash equilibria include two points, 0, 0, and 1. So when it's 0, 0, it's clear that it's the equilibrium because nobody can change this by playing anything, because the product will still be 0 if only one player deviates. Now, then think like that. If at least one player plays something positive, then the only way to best respond to the other player is to play positive. Therefore, the only Nash equilibrium besides 0, 0 can be when they both play. Excuse me, the only best response to a positive play is playing 1, the highest possible positive number in this game. So the only Nash equilibrium when the players don't play 0, 0 is maybe 1, 1, and let us check, is it a Nash equilibrium? Yes. It's the best possible, everyone best responses here. So there are at most those two Nash equilibria, and as I have said, we have also checked now they are Nash equilibrium. So this is the set of all Nash equilibria. But now let us forget all these complications. The set of Nash equilibria here is not empty. Now another infinite game we also saw actually is the same as the first one, where the strategies are not the closed segments between 0 and 1, but the open intervals 0 and 1. And here there is no Nash equilibrium, because for any strategy of any player it had to be positive. The only best response, there is no best response, because there is no largest number. In particular, there is no Nash equilibrium. So we have seen that for both finite and for infinite games, we can either have or not have Nash equilibrium, so there is no simple way to say when we have it or not. But let us try to study this, and as I said, when we do know it exists, we will see, for example, some cases where we know it exists, but it will be, and we won't see why, a hard problem to actually find it in general, so we won't study that. And the agenda is as follows. First of all, we are going to study a very interesting theorem about sufficient, not necessary, sufficient conditions for existence in infinite games. Then we are going to ask what about finite games. So first we are going to define a notion of mixed extension for finite or infinite game, does not matter, which represents a probabilistic plane of strategies. And then we are going to formulate and prove the famous Nash theorem, which says that for any mixed extension of a finite game, there always exists an equilibrium, at least one. So that will be another existence result, which actually will use the first one, because the mixed extension is always an infinite game, well, unless the original game has only singletons for strategies, in which case it's not interesting to talk. But anyway, so mixed extension is an infinite game, and the first theorem for sufficient conditions for the existence of Nash equilibrium in infinite games will allow us to prove the theorem of Nash. By the way, this is not how Nash proved it. There is a certain similarity, but it's not the way he proved it. We later, if we have time, we are later going to see the way which is closer to how Nash actually proved it. And finally, we are going to see a nice example for a certain Nash equilibrium with irrational probabilities. It's a very nice example to see. Okay, so let us start with the existence of Nash equilibrium for infinite games. So, first let us formally look at the idea of best responses and the connection of that to the idea of Nash equilibria. So, remember what BI is. So, let me remind you, BI we defined, I think we did this, the best response correspondence. So, given what the others do, S minus I, BI goes, oi, I have made a mistake here. It's not, well, I've written it as if it's a function, but it's not a function. It gives a subset in general. So it can be even seen as a set function, so to speak. But I prefer to have the normal notation of a function. So let me change that. Let me change that. So BI does not go to the set of strategies. But to a set of subset of Si, and so does BS. So the best response correspondence takes the strategies of the other players and gives gives you the set of your strategies which are the best possible. So at least in finite games, that's always well defined. If in an infinite game, it can be empty, by the way, that can be that there is no such strategy, but at least there is a subset of the best possible strategies. And so it's a subset of strategies i's as I, such that si with s minus I is at least as good as any other ti with s minus I. And as I said, if it's a finite game, you always can find a best. You always can find something which gives you the maximum value of futurity. If it's an infinite game, not necessarily. And now B, without the index, the subscript I, it takes a set, it takes a strategy profile and gives you a subset of all strategies, which is the Cartesian product of those best responses. So, given a strategy profile, everyone in the same time tells I would prefer in this case to do that. And then they all do that. That's the BS. Not like bullshit, but BS like the best response. And then Nash equilibria is the set of all the S's such that they are in the set of their own best responses. So all the profiles which are a best response to themselves. Not necessarily the only one, but a best response. Of course, if at least one of the players does not have a best response, for example, as I said, this cannot have to exist for an infinite game, clear, then there is no profile which satisfies that. But even if all the players have best responses, it does not mean that you have a Nash equilibrium. For example, in the case of match in pennies, it's a finite game, so every player has a best response, but There is no strategy profile, which is a best response to itself. Okay, so we in a way need a fixed point of this function. Well, a fixed point is usually a point which is not moved, but here in this set, it's a point which belongs to its own image. In this set, in this sense, is the fixed point, and therefore we're going to use fixed point theorems. So theorems which assert existence of fixed point to prove existence of Nash equilibria. And Nash used another fixed point theorem from what we are going to use here. He used the famous Brouwer's fixed point theorem. We are going to use Kakutani's. That's what Osborne and Rubinstein write in their book. So you're welcome to consult their book if you want. So in the case of Kakutani, that's the theorem that we are going to use without proving it. And that's that if you have a non-empty subset of the a finite dimensional Euclidean space Rn, and that X is compact and convex, and we have a function from X to the set of its subsets. So for every point it returns a subset. By the way, that's going to be topological. It's not the main theme of the course. So if you don't like this, don't be afraid. Don't be averted from the course because of that technical thing. They're not going to delve into those fixed point theorems beyond what we need from them for our goal. But you need to understand what we say here. At least try to. So if we have a compact convex non-empty subset and a function f such that every point gives a subset fx which is convex and non-empty, and the graph of this function f is closed in the sense that for any two sequences xn and yn such that yn is in the set f of xn for any natural n. So we have a sequence of values in the domain and of a value in that fxn, and both sequences converge. So the limit of xn is some x, the limit of yn denoted some 1. Then also in the limit we have that y is in the image of f. It's clear that both limits belong to x because it's compact, and compact in an Euclidean space means that it's closed, but it's not clear that if every yn is in the f of x, and then also the limit is going to be in the f of the limit, and that's the requirement. That's what we call graph is closed. And if we have this convexity and closeness conditions, then the theorem states that there exists a point in x which belongs to its own image. There exists such a fixed point that we need. And that's what we're going to use for our way. Not our, it's Osborne and Rubinstein's at least, or maybe they used it, took it of someone else. But anyway, for this way we are going to present first of proving the theorem of Nash. But first, that's a theorem. Oh no, actually not the theorem of Nash. First we're going to prove another theorem, and then we're going to use it to prove the theorem of Nash. But anyway, first of all, let us notice that none of these conditions can be dispensed with. We cannot say like that this theorem is wrong if we remove any condition, that f is suddenly not empty, not convex. Excuse me, if f is not convex, or if f is empty, or if the graph is not closed. If you remove at least one of the conditions, you can always show a counterexample for this theorem. That's important to know. And now let us prove the first existence theorems of equilibria, of Nash equilibria. That's not the famous theorem of Nash. That's a theorem of existence sufficiency condition for existence of Nash equilibria, which is not the theorem of Nash. And first we need to definition. So first of all, a preference relation. So now we'll talk about a general preference relation. In particular, of course, it can be the preference relations that we use, that we show using the utility functions, because we assume the assumptions of von Neumann and Morgenstern, under which we can, by their theorem, use the utility function. But in general, we can speak more generally here. That's why we can speak in the language of preference relations. And again, don't worry if you don't like this language. We are going to speak most of the course in the language of utility functions. So a preference relations of a set S is called continuous if for any two sequences x, n, and y, both of which converge n when for any n xn is preferred to yn, also the limit of x is preferred to y, the limit of y. So if you have a preference of x or y, then the same preference holds in the limit. That's the notion of continuity in this case. And now we're going to define a bit of a weird notion, but again, we are not going to use it all the time. A preference relation over the set S is called quasi-concave on Si, not on S, on Si, if for any S prime in S, the set of all the S's in Si, which gives to I at least what it gets in S prime, is convex. You may need to stop the video and see it again, but again, it's not something very intuitive, but it's not even important. It's important that you do understand what we define. So a preference relation over the set S, which is in this case assumed to be a Cartesian product of size, it's called quasi-concave on Si if for any profile in S prime, S star, the set of Si's such that given S star minus I, using Si gives I at least what it gets over a star, the set of all the ways for player I to get at least what she gets in a star is convex. And now we're going to formulate the following sufficiency theorem that given the game of n players, strategies S, and preference relations, again, we're going to formulate in a very general way. We don't even need to have to assume von Neumann Morgenstern here. So it's even stronger than what we might want, but okay. A sufficient condition for non-empty Nash equilibrium set. So where exists a Nash equilibrium if for any player, the set of strategies of that player is a subset of some Euclidean space of some dimension, and that set of strategy is non-empty, compact, and convex. Please notice convexity already means that that this set is not finite. Well, unless it's only one point. So unless it's degenerate being 1 point, convexity requires that any 2 points can be connected, and that's therefore only a theorem for infinite games. Okay, then every preference utility preference relation has to be continuous, and we define what it means, and any preference relation has to be quasi-concave, and we also define what it means. Now let us prove this theorem using the theorem of Kakutani. And of course, given that we know that the existence of Nash equilibrium is equivalent to the existence of a certain fixed point, it's not surprising that we use the theorem we've just formulated for the existence of a fixed point. So the proof is as follows. Just need to show that all the conditions of the theorem for the existence of fixed point of Kakutani hold. So for any player I and any strategies of the others, S minus I and S capital minus I, the preference relations is continuous, that's what we assume, and SI is compact, that's what we assume, and therefore, for topological reasons, that's a famous theorem in topology, the best response sense is not empty. Okay, so now, calling the definition of quasi-concavity, which is not simple, but still it means that some set of something not worse than of a player is convex, we can show that the best response to Si, S minus I is also convex. And from the continuity of the preference relations of play I, which we assume, we can prove that the graph of the correspondence B, best response, is closed. Therefore, all the conditions of the theorem of Kakutani are fulfilled, and by the theorem of Kakutani, there exists an X star which belongs to its own set of best responses. So there exists a profile which is its own best response. Not necessarily the only one, but it is a best response of itself. And therefore it means that it's an Nash equilibrium, and we have proven that there exists a Nash equilibrium. Okay, now let us make two important remarks. The first one is that there exists at least one Nash equilibrium, but maybe more. And indeed, maybe more. And another one is that, as I said, no finite game, well, with more than one strategy for at least one player, satisfies these conditions because of convexity. Okay, let's look at a real life example. That's a simple thing, that example from my doctorate actually. So that's a real life example, and that's a simple example of using this theorem. That's an immediate example, so it's not something complicated, but it's nice to see how this theorem is used. So assume we have n players who are students and they have a time budget each, and they share these time budgets between a certain set of projects. A project can be a project, or it can be a course, whatever. But better to talk about projects because it's something that people do in common. So a project can get time from several students. Therefore, it's better to talk about actual projects. So say software project from 1 to P. And therefore, the set of strategies is all the vectors of players I, such that the vector is non-negative, so that's the time the player spent. And the total, so the upper index is the player, the lower index is the project in which the time is invested. And if we sum of all the projects, the x of the given player, that it's at most the budget of the player. So all the ways to distribute your budget, which don't exceed the budget, are all the strategies you have. And the value of the project is given by a function which receives those vectors of contribution. So from each player, what is the contribution? And gives a non-negative number, what is the value of the project? How much does the project is the project for? As you can guess, this can be, of course, used not only to students who divide their time between projects, but also to scientists who divide their time between papers, or I don't know, writers who divide their time between books, or investors who divide their money that between several companies, so it can be used for any sharing of effort. That's why it's called an effort sharing game. So it was, I think, first modeled in a certain way by Bachnach, Sirkanis, and Voinovich. So that's a very generally applicable game. And here we're looking at a very toy example, but it's a nice example of using the theorem. So we have a set of players. We have divided the set of strategies are all the ways to split the time budgets, or whatever budget you have between the projects. Now the value of a project is given by a function, and each project receives, each player, excuse me, receives a share from this value of a project, and it does not have to equal this value. So if you sum these shares of all the players from all the shares that all the players get from project J, are at most what the project is worth. It can be less, so it's so-called free disposal. It does not have to be equal to the worth of the project, it can be less. And we assume that the functions f are continuous, so there is no jump in what you get, and they are concave. For example, the quadratic function. And, excuse me, no, that's convex. They are concave. For example, the logarithmic function. That's an example. And finally, the value of a player is simply the sum of the shares that the player gets from all the projects. So we have defined the game. You have players. You have the sets of strategies, and you have the utility. That's a game in the strategic form. So what about the existence of Nash equilibria for this game? Well, it does have a Nash equilibrium, as you can guess, and we are going to use the theorem we've just proven. So let me remind you the theorem. We need to show that every strategy set of a player is non-empty, compact, and convex, and the preferences have to be continuous and quasi-concave. So every strategy set here is non-empty. You have some budget which is non-negative, so you have at least one way to divide it. The set of all the divisions of budget, such that the sum of those coordinates is at most a budget, is compact. It's closed, and because it's closed and bounded, and it's convex. And now you can prove it. I don't prove it here exactly, but you can of course prove it. It's a simple statement from infinitesimal calculus, and each utility function is continuous, so it's the sum of fij's, and therefore the preference is continuous. And the final thing we need to show is that the preferences are quasi-concave. And I remind you that it means that for each strategy profile, the set of all the SIs, such that they give player I at least what the player gets from the strategy profile, has to be convex. Now why? Well, in this case, to give it at least what it gets, it means that the utility function of player I, when it uses SI, is at least what the utility function is when the profile is a star. And that is convex because, okay, so the sum of concave function fj, we assume fj is concave, is also concave because it's the sum of a concave function. Therefore, the set of all the SIs, where the UI of si minus I prime is a star, is at least the UI of a star, given that UI is a concave function, the set is convex, and that's what we need. And therefore, all the requirements of the theorem hold, and this game does have a Nash equilibrium. I think that you realize it's not clear what is the equilibrium. It's clear that you want to use probably most of your budget. It's never bad to use all your budget. But is it like, well, actually not necessarily. I've not defined here. I have not said that it has to be non-decreasing function. So it's not even clear. In this general formulation, it's not even clear you need to use all your budgets. It's definitely not clear how you can see that there is an equilibrium. What is an equilibrium? But at least they have proven that it's in the most general form, there always exists an equilibrium. Okay, now let us talk about finite games, because we've said that we've proven a theorem which gives a sufficient condition for the existence of Nash equilibria, but it will not work for finite games.